Hi, got an interesting little bit of kit to look at today. This is a thermal imaging camera designed for firefighters. The idea is that they clip this on their helmet and sort of walk around looking for people in sort of fire sites, because this actually gives quite a good view through smoke, so they can see bodies. They can also see bits of burning embers and so on, things that are above a certain temperature. So unlike a conventional sort of thermal imaging camera, it's actually got like a head-up type display here, and it's got this clip that clips on the helmet, and it's pretty damn heavy. I think it would actually be pretty uncomfortable to walk around for any serious amount of time with this around your head. It's got this sort of strap, so presumably you sort of go like that and then clip it on when you want to use it. Bought it on eBay. Solder's not working, so we'll take it apart and see if we can get anything happening with it. Well, we've got the lid off. See one rather interesting shaped PCB. I wonder if they built something else using that middle section to avoid wasting it. I'll just have a quick look around this. Not really much. There's battery contacts under here, some buttons. There's the head-up display there, and at this end there's a connector, and I believe that's to connect an external video monitor. There's what looks like a very expensive LEMO connector on there. See, there's some inductors on the underside of the board, and actually these look like they've actually detached to some extent. Maybe this thing's been dropped, and perhaps that's what the fault is, hopefully, because that could be a nice easy fix if so. I actually heard a bit of rattling, but in fact I actually noticed there's a pack of silica gel in there as a desiccant to keep moisture away. There's quite a big chunky metallic lump here. No idea what that could be. That's next to the back of the head-up display. Bit of flex here, presumably from the display. And around here we can actually see this is the actual camera head. Sort of lens and camera assembly. I don't know whether this is cooled or not. There's a shielding covers. This is probably the front end analog stuff under this metal shielding to avoid radio interference. Because obviously these things could be used with quite a powerful radio nearby, and fire brigade radios can be sort of 5 or 10 watts, so they could kick out a lot of interference. Alright, just stick a battery on, and there's actually no on-off switch at all. This just turns on when you connect the battery. The idea is it's a really simple to use, sort of just pick it up, stick the battery in and go type of piece of kit for use in emergencies. I can hear a slightly sort of squeaky inductory sort of noise. Now there's a click going on there. Now what that's going to be, thermal images almost always only sense temperature difference, so what they usually have is a mechanical shutter which has got a temperature sensor on it, so they can measure the difference between the scene that they're looking at and the temperature of the shutter. So what you find is sometimes you either get a periodic click as they do this calibration. Some of the higher speed ones actually have a rotating shutter in front of them, but this one clearly you can hear it clicking away, so it's probably doing its calibration. A few little green LEDs on here that you maybe can't see, just flickering on and off. But I'm not seeing any light or anything coming through that head-up display at the moment. And we'll just stick a scope on that video connector just to see if there's any sign of any signals on that. And you can actually see the shutter here moving in and out. And on this video connector is what looks like a composite video signal. Can't see any obvious motion in it though when I wave my hand in front of the camera. There does appear to be some little blips here which might be some indicators, so we'll connect this up to a monitor and see what it's trying to tell us. Well, I thought that LEMO connector looks a bit familiar from quite a few years ago. I was doing some work on, coincidentally, some fire brigade related equipment, and I just dug out the old box of all the bits relating to that project, and look, we have the right connector. Right, I've connected up to this little car monitor, and let's see if it's going to talk to us. Oh, yeah, that's red stream. Ooh, diagnostic error, I2C device failure, detector board, I2C received timeout error. Still running self-test. Initializing system. Det board bad v reset failed. Sounds like it might be consistent with the power supply issue, possibly due to a coil having fallen off. So, oh, we're just getting a white screen. There's no response. Waving my hand in front of it. Right, just taking the board out. Nothing really interesting in the lid. There's the rubber membranes for the buttons, springy battery contacts, optical assembly. There seems to be some sort of parabolic lens. The desiccant, and just the back of the video connector. Right, so the other side, the main board, you can see we've got these power supply circuits here. A couple of slightly detached inductors, although I don't think the wires have actually come off those. I'll test those a bit later. And this is the display unit. I'm not really quite sure what's going on with this big lump of can. It's very solidly machined. It looks like this has been machined out of one big chunk of metal. Looks like it's some sort of thermal interface material. No, not quite sure what's going on with that. And you've got the thermal imaging section here. You've got the back of this board with these big chips on it by the looks of it. A little bit of earth braiding onto that screw. Again, this big, not the big sort of solid chunky piece of metal, and I'm not sure if this is solid or hollow. Looks like it's sealed around the outside with some sort of rubber sealant. Not sure what's going on with that. And then there's the actual camera headboard here, and you can actually see now how the shutter works. Just a solenoid that pulls that shutter into there. Incidentally, the lenses of these things aren't glass or anything, because the long wave infrared doesn't go past those. This has actually got a germanium lens. There's only about 3 materials that will transmit that waveform. There's germanium, zinc selenide and sodium chloride, common salt. Obviously salt has some slight lifetime issues when it gets wet, but I think germanium is pretty much the standard for most thermal imaging applications. Right, I found out why that display wasn't coming on. This connector has been plugged in offset. Now I suppose it's conceivable someone might have done that deliberately to disable the display, or maybe they just put it back together wrong. So that might explain at least part of the thing. Just the display module. There's a Sony liquid crystal module. It seems to be very sort of heavily heat sinked onto this backing. I'm guessing this is the backlight here. Oh, interesting. Date wise, I did see a date stamp of 1998 in here, so it's a fairly old thing. Now this isn't a LED backlight, it's actually some sort of gas discharge device. You can see the little evacuation pip there. Now I've seen a device like this before in a film scanner, a film negative scanner. Obviously nowadays you just use LEDs, but this is a curious bit of slightly vintage backlighting technology. Just notice this little device here. I think that's a light sensor. There's a little hole in the back of here, so I'm guessing that's poking through to monitor the backlight intensity, so you can adjust the drive. Obviously being some sort of vacuum device, that thing probably ages, so they maybe want to control the drive level according to its age. I'm still not really sure what's going on here, and this doesn't seem to actually have anything in it. Because of the heavy structure, I'm just wondering if this has maybe got some sort of heat absorbing material in it, sort of possibly even, you know, water or something, to actually absorb heat so it can run for a certain amount of time without, because obviously there's not much scope for external heat sinking on this thing. Never really seen anything like that. I can't really think what else it would be. It sort of seems to be sealed. There's no electrical connections into it, so that's, I think, just maybe that's a filling port or a mounting screw. So I'm just wondering if that's actually got something in it to absorb the heat and then release it again over time, so it can run at high power dissipation over a short period of time and then have a recovery period. Interesting, because I was wondering the can over on here, again, that looks like it could be a sealed can of some sort. Strange. I've taken this screw out, and there does seem to be some sort of sealant on the thread, and there is an O-ring in there, but I think there's also sealant inside. There's no, it feels fairly sort of solid. No sign of any liquid on there, I don't think. So I think it's just been, something's been put in and then they've just gunked a load of sealant into it, I think. But I can only assume that's some sort of thermal absorber. Well, this is the actual image sensor head. Something interesting I noticed. It looks like a sealed off copper pipe going into this bit, so I wonder if that, well, I mean, there's a few things that could be. It could be some sort of heat pipe cooling system. Maybe it could be part of the lens assemblies in a vacuum or gas or something. The side here, I'm guessing this is probably a temperature sensor on the side to measure the reference temperature on this outside. I can't actually see a temperature sensor on the vane, so it could be they just assume that whatever the temperature of this is, the shutter's at the same temperature as their reference. That looks like sort of thermally conductive stuff. Not sure what it's actually doing. It doesn't seem to be, unless there's a thermistor on the PCB underneath that perhaps. Yeah, actually there's a little surface mount bit. I'm guessing that's probably going to be a thermistor, and this is heat conducting stuff so the thermistor can measure the temperature of this back plate. And again we've got what looks like this enclosure with a sealing screw on it. I actually wonder whether this, you know, it could be to store heat generated by this, but being fire brigade equipment, it may well be that this is actually designed to give it tolerance against external high temperatures, because I know a lot of fire brigade stuff has to withstand obviously high temperatures, smoke, fire and so on. So maybe it's just to keep it stabilised more towards the external temperature. I'm not really sure about that, because I mean I wouldn't expect that LCD to kick out a great deal of heat. So I wonder if it's actually more about stabilising its own temperature to keep a good display. There's not much on here, there's a few odd components here, but not really a great deal. And it looks like there's these metal feed through from this enclosure, so this enclosure does definitely look sort of quite sealed off by this sealing thing, but whether that's liquid or gas or vacuum I really don't know. Yeah, and this actually looks like it's a wire wound part, so hard to see, but this does actually look like it's a wire wound part, so I'm guessing that's probably a platinum temperature sensor for sort of accurate temperature measurement. Right, this is this little vertical module I've taken off, a couple of PCBs. That's interesting. This one's got a great big huge chip that's not fitted. Right, I've taken a very close look at this board, and it looks suspiciously like someone's taken some chips off of it. Now, although these joints here are plausible as having had solder paste but not been soldered, if you look over here you can actually see some remnants of pins. Also on this large chip, again, a lot of these joints look possibly plausible as ones that have never soldered, but there do seem to be some, it's a bit hard to see on this one, but even more suspicious on this connector. The first thing that's a bit odd is that there are some pins that are left out, and there's no real obvious reason for that. It does look a little bit bent, but again on the pins that are missing you can actually see sort of residues of the shape of the pin. For example, that one there. There's clearly been something on that pad, but I'm a little bit at a loss to figure out how that pin came out, and it's now sort of not even there. It's really weird. Yeah, this is actually cut and pulled out. Now I suppose it is conceivable that this board's been heavily modified for use, yeah, maybe a board that was in a different system and they've chopped some pins out for some functional purpose. But also if you look on the other side, again there's other chips that look like, yeah, they were actually there at some point, and it's conceivable that it's a stock board that they take parts off for this particular model, I suppose. but that does sort of lead me to think that maybe somebody's been in here and had a go and nicked some parts out of it, in which case it's going to be extreme teardown time, but I'm going to persevere and see if I can get any sort of life out of it. Right, it's a real pain to actually power this thing up because the battery clips onto these connectors, then these just press onto the pads on the board. So I was looking at ways of improving that, and it looks like they've actually provided edge connector strips for a test jig. Now, in a second, just truly awesome, unbelievable coincidence, I was looking in my box of random edge connectors, which, you know, I very rarely use edge connectors, and I found this. I have no idea where this came from. This, I could have easily have had that for 20 years sitting around, and it's exactly the right pitch and exactly the right fit. I mean, what are the chances of just happening to have two oddball connectors for the same bit of kit? That is just incredible. I'll just quickly take one of the batteries apart. Just a pack of 4 nickel metal hydrides, and it's got a battery management BQ 2014 battery manager in here. There's not only a temperature sensor but also a thermal cutout in the middle of it, so that's fairly belt and braces. I'm not sure whether or not it'll work with that battery manager out, so the first thing I'm going to try is just apply power and see what happens, but failing that I can always just solder up some leads to this battery pack, so I can still put it in the charger to charge it and then plug it on without having to mess about with all these spring contacts. So let's just try applying simple power and see what happens. Alright, let's fire this up and see what happens. It seems to be... Ew. Same sort of start-up display, pulling about 2 amps. I was sort of expecting this to have pretty high power consumption. The clue is probably the fact that you get the charger assembly takes 4 batteries. So we're getting pretty much the same messages, so doesn't look like it's really complaining. In fact, it's even actually got a little AC line signal on there, so maybe it's recognised that it's not seeing the battery manager and assuming it's being powered externally. Well, look what we have here. I just sort of turned it round, powered it up again, and we have thermal images. Let's see what a soldering iron looks like. Oh, very hot. So it looks like there's just a bad connection or something that was stopping this thing working. It didn't give any error messages when it powered up. And we appear to have a thermal imaging camera. So it looks like those missing components off the board, I mean, I wonder if those were maybe some parts from a different model and they modified, cause I know they discontinued this model, so maybe they didn't want to commit to doing sort of huge amounts of new boards for a new product that was a bit tentative, so they modified something out of an existing product. So I'm very happy. I probably may well have some intermittent faults to track down, but the fact that it does work clearly means that there aren't actually any bits missing. Right, I'll just put a little an external light behind this LCD, and you see the little LCD is actually working. It's just there's a problem with the backlight, so, and if I did want to get this working in head-up mode, I could probably just replace that. I'm guessing that backlight unit has probably died, so I'll probably just replace that with a bunch of LEDs. It does seem to have very good sort of sensitivity to different temperatures. This thing does seem to be quite twitchy. You give it a little tap and it starts flickering and cutting out, but what's interesting is that the little display doesn't cut out, so that, at least that intermittent fault, looks like it's only affecting the video out and not the actual imaging side. It's still actually taking images and displaying on the small display, so that fault at least shouldn't be too difficult to track down. Well, I think this explains the intermittent video. There's 3 pins on the video encoder chip that seem to have been graunched by something. Don't think this explains the other faults, because these are just the video outs. They're not sort of I2C or power or anything, but we'll fix those up and see if there's anything else we can find. Right, I've noticed it fairly consistently works when it's one way up and doesn't work when it's the other way up. Now, that message about I2C detector test, I noticed there are a couple of 24C01 E2 problems on this unit, one on the bottom board and one on the sensor board. Now, guessing the sensor one is probably device ID, or maybe some sensor calibration data. So one thing I checked is when it's in its not working mode, the actual supply voltage, that chip appears to be missing. When it was working I was getting 5 volts on it, but this is in its not working mode. I'm only getting 1.1 volts, so there's clearly something up with the power supply to that chip. So I need to start tracing that back. So look at the other one. Right, we've got 3.5 volts on the one on the bottom. I've verified that they both share the same bus, I2C bus, the one on the bottom board, just down here. So they're both on the same I2C bus, but one of them isn't getting power in its not working mode. So I need to try and figure out where the power's supposed to be coming from, and see if we can do anything about that. Right, I've hooked the scope up to that power supply line, so just do a bit of tapping around, see if I can make it glitch. What I'm doing here is a quite useful way for if you've got a really sort of flaky intermittent fault, is sort of just tap with a screwdriver, and you can sometimes find that you can actually locate the fault. You sort of tap lighter and lighter, tap it until you start getting the fault to manifest itself, and then just sort of get lighter and lighter, and you can quite often actually locate it fairly closely. Although obviously you do get some mechanical vibration through the board. The other method is to apply sort of slight stress and twisting to the board as well to see if you can locate it. So let's see if we can actually get this fault to manifest itself while it's in working mode. So I'm just going to try some gentle twists on the PCB. Interesting. Got something there that seemed to coincide with the solenoid kicking in. Oh, there we go. Right, I can actually twist the board and get that to very consistently drop out, on, off, by just applying a very gentle twist. What I was doing there was just sort of applying a slight twist. You can probably see it on the monitor actually. So I'll just bring it, so I want to twist the board, there it goes, then it's back. Now the trick here is to try and narrow it down. I wonder actually, this is a very thin part of the PCB, so there's probably quite a high stress concentration here if it gets dropped, or yeah, there's any mechanical stress. It does seem that twisting around here does seem to be bringing it on quite easily. Doesn't seem to be too sensitive to vibration, it's mainly the twist that's doing it. I think I'll take a close look at that board. Actually, there is quite a large resistor very close to that. See that? There's quite large resistor quite close to that, and that's a really bad position to put a large chip resistor right onto the maximum stress point of the PCB. So let's see if that's actually connected to this node that we're having problems with. Actually, let's just I'll just try measuring the voltage across it while I flex the board. That might be a way to tell whether that resistor is going open when the board flexes. Quite low value, 0.04 by the looks of it, so it's probably a current sensing resistor, so it's entirely plausible that that could be connected in series with a power supply. And so if it's cracking, then there's no significant voltage across it at the moment. Let's see if I can twist it into failure mode. Oh yes, look at that. When I twist it, the voltage across that resistor shoots up quite significantly. So I suspect that resistor's maybe got a crack in it. Let's try replacing it. Right, replace that resistor. Not surprisingly, I didn't have any 0.04s in my stock, but I had some 0.1s in two different sizes. So there's two 0.1s in parallel plus two in series across it to give 0.4. Unfortunately, that wasn't the problem, because when I twist the board, it's still freaking out. So need to carry on looking. Right, I'm still trying to figure out where this supply comes from that's disappearing. Now, I was just poking around in the area of the board, and I found this other supply that also dips when the board's flexed. Now that's the green trace, the yellow is the 3.3 volts I've seen disappearing. Now this is quite interesting, because you can actually see that what happens on the green trace happens first and then the yellow follows it. So clearly that 3.3 volt supply is probably derived from this green supply, so it's actually the green one that's failing. You also notice that you've got a fairly much faster fall on the green, and also a very fast rise, which suggests it could actually be this one that's actually becoming disconnected, and the slow fall will be down to capacitance on there. But if you compare the rise times, the green is rising almost instantly, whereas the yellow's taking a little bit of time, so the green looks much more like it's a connection that's being broken and open again when the board gets flexed. So hopefully we might be getting a little bit closer. And that green trace was on this rail here. Obviously by the thickness you can tell it's a power supply rail. This connector here goes up to the image sensor board, so this is probably supplying one of the power rails to the image sensor. So we'll see if we can find out where that comes from and try and track back to where it's being broken. It's also conceivable it could be this capacitor going short intermittently as well. Right, now we've found what looks like probably the supply that's being broken. I'm going to see if I can figure out where that's come from. So all I've done is I just hooked up the meter in continuity mode to that node that we know is falling, and then because it looks like a power rail, the chances are it's going to be coming from one of these power supply sections, and obviously that'll have a local capacitor. So I've just been sort of probing around. Obviously when you program your continuity, you sometimes get readings which aren't true continuity. You sort of get some false alarms, especially when you've might have a little bit of voltage left over. But this one here looks promising. This one's reading 4.7 or 4.2 ohms. I did notice there's also a little inductor on the back, so my guess is the power supply is coming from there. I'll just probe that inductor. And on this inductor, right, so that supply is definitely coming through the board onto that side, and we've got the other side. Obviously it says L2, so that's how we can tell it's an inductor. And actually, that looks like it's actually open circuit. Let's just flex it and see if we can get it to make contact again. Yeah. So our break is between here and here, so this just looks like a ferrite bead inductor. So my guess is that is the problem. So let's replace it and find out. Right, let's replace that inductor. Because it's in a power line, the value isn't likely to be at all critical, so pretty much anything's likely to do the job. So let's fire it up and see what happens. I need to prop it up a little bit so the shutter doesn't stick on the bench. Right, so that's working. Let's flex it, and now it seems to be quite happy being flexed. That screen blanking is when the shutter's dropping, but that we appear to now have a working non-intermittent thermal imaging camera. Yippee! Right, now I can actually run this thing with the board this way up and get at the buttons. Now just flip the button to turn it into colour mode, so you get the more sort of conventional thermal imaging colour graded display there. There's a nice hot soldering iron that's coming out as white. Buttons, see, originally I thought the buttons weren't working, but it seems you just have to press them for quite a long time before they do anything. Right, there's also a range button which I'm guessing affects the temperature range, so try pressing that and see what happens. Alright, that's saying high. Actually seems to have made a lot of difference. And let's try low. Yeah, it seems to have made a little bit of difference, but not a great deal. Right, let's try the buttons marked rad and cal. Rad just seems to make this indication turn off. Not quite sure what that's about. It seems to be saying under, but it does sometimes give some figures. I think maybe that's a temperature indication for this centre spot. Yeah, so if we put the soldering on that centre spot, we see it's now saying over, so pretty over temperature. So that's probably giving you a temperature indication on that particular area. Maybe if I change the range, I'll get a different. So that's on high. Yeah, 301. Yeah, that's probably the temperature actually. 307 degrees. See, this monitor, the edge is slightly off screen, so I'm guessing that's actually telling you how hot that is. 235. That's fairly plausible for soldering iron. That's in the high range. Let's get it on the low range and see what it does. No, it's still saying under. We can't seem to get a... I'm sure I did see that giving readings of sort of body temperature when I was testing it last. Maybe there's some other permutation that I've not got happening properly. I think that cal button might just be forcing it to do a shutter calibration. It seems to be fairly almost random, these shutter calibration things. It seems to sort of do it when it feels like it. I suspect the cal, yeah, the cal seems to just be a way of forcing it. I think it's maybe, you know, looking at the content and figuring out whether or not it needs to recalibrate. It may also be dependent on whether it's seeing temperature changes on the temperature sensor around the lens. I'll just stick my finger on that temperature sensor. Right, let's look at this loose coil. I'll just pull this apart and either replace it or stick it back together, I think. Yeah, it looks like the actual coil and bobbin's intact. All that's happened is the bobbin's just come unglued from the base. So I think I'll just glue that back on rather than replacing it, because I haven't got one that's the same size to hand. Right, before I put all this back together with all the shielding and everything, just take a detailed look at these boards. This is the front end board, so the image connector connects here. There's all this missing stuff that we've seen before. These look a little bit odd. I suspect these are some precision film resistors or something. These look a bit weird. I've not seen resistors like that before. Maybe they're designed for laser trimming, although I can't actually see any signs of having been trimmed. But if this has been a board that's been modified, maybe, and these actually go to this chip that's been taken off, so maybe they left the resistors off and didn't trim them. This is the main AD converter. This is an AD9240, which is a 14-bit converter, 10 megasamples per second, so that's going to be converting the analog signal out of the image sensor. There's a 24C01E2 bro. All the boards seem to have these 24C01s on, which I'm guessing just like a board ID, and just so the thing can check the system configuration, make sure the right sort of boards have been plugged in. There's lots of these big orange tantalum caps all over the place. One thing I just noticed, because there's no markings at all on them, but the positive marking, they've got this little spike on one end, and that appears to be the positive marking on it. It may also be part of the production process, but so I've seen these caps occasionally, not often this big, but I hadn't noticed that little spiky thing before. One slightly interesting thing is the date on this is 1999, but the board it plugs into is actually 1998. So I think my guess of what's on here, I would guess that is either an old FPGA, because I know that some of the old Xilinx FPGAs did come in a PLCC package, or a DSP combined with a little bit of RAM. So I'm guessing this came out of one product and they've sort of adapted this, because this My guess is this may have been a bit of a speculative product, so they might not wanting to commit to fully custom boards for everything, so I think they've maybe done a bit of a mix and match of boards out of other products just to get this product out there to see if there's any market for it. And I think they did discontinue it and passed their firefighting stuff over to MSA, who specialise in firefighting gear, so maybe they figured out that this thing was a bit too big and heavy to be useful, and the firefighter ones now tend to be the more pistol shaped, fairly relatively conventional thermal imaging cameras. Let's look at this logic board. This is a Motorola, who are now called Treescale XPC823. This is a PowerPC based microcontroller. Also up here is what I suspect is a 32K watch crystal, which of course is a bit odd because this product doesn't have an internal battery or real-time clock, which again is suggestive that this maybe was a board from a different product that they've adapted. These are just resistor packs. These are flash memory, which will obviously be the program code for there. There's a header there, I'm sure this will be a JTAG programming header for the processor. There's 3 RAM chips, FPGA, which is going to be handling the data from the sensor. One thing which I think a lot of this RAM's for is, I was reading through a few sort of documents on similar products, and the shutter, as well as being for absolute temperature measurement, it's also for correcting differences between individual pixels. One thing I noticed when I was playing around with the fixing the fault was that sometimes you get like quite a random pattern slowly building up on the sensor, and then when the shutter calibration happened, it would then disappear. So I think there's potentially quite a drift between literally from pixel to pixel over time. So what they do is they take a known dark shot using the shutter and then subtract that from all the image pixels. So there's probably enough RAM in here to store that map, and obviously the FPGA is going to be doing the subtraction in real time to produce the real pixel image. There's an IDT, there's another SRAM chip here, another 24C01 E2 PROM there. There's some connectors, none of these are used, again perhaps in a different product. These are used for user interface connectors or something. And there's not really anything at all on the back side of the board. There's just this fairly high density connector. Again, this is a tweak that basically what that's doing, that's going from ground through this screw, and then one of the there's a shield that goes between the sits over the board. That's one of the mounting pillars. So that's just providing it a ground, and it's done in braid to keep the impedance low, so it acts as a decent RF shield. Not a great deal on the actual image sensor board. It looks like the sensor, or at least these gold coloured pins, are soldered straight to the board. This whole sealing thing, I think my best guess is that it's a vacuum and the sensor itself is actually suspended in a vacuum to minimise any thermal leakage into and out of it, because obviously you're trying to build a thermal image on the surface, and what you don't want is any ambient affecting it, but also you want the thermal mass to be very low. So I would guess that if we took this apart, which I'm certainly not going to, you might find it may be suspended on some very thin wires and in a vacuum to avoid any internal convection currents messing up the image. If somebody knows anything about thermal imaging sensors, feel free to add something in the comments to let us know. The rest of the stuff on here is analog. There's a few sort of op amps, and there's a comparator and a few other odds and ends, but there's nothing. This is obviously just the stuff that really needs to be close for electrical reasons. There's another 24C01 on there, of course, which is the thing that actually kicked off the whole fault finding trial, and there's a little D to A converter there, which again is probably for setting some sort of bias or something. Well, I've done a little bit more digging, and I think I figured out what all this stuff's all about. Some of the product literature talks about thermal phase technology, which I'm guessing is some sort of material that changes from either solid to liquid or liquid to gas with quite a high latent heat, so it absorbs heat. Now, this isn't to do with absorbing heat given out by the products, because in a firefighting environment the environmental conditions are very harsh, so the idea is that this can actually accept quite a high amount of external heat before the temperature of this and also the temperature of the LCD increases to the point where it stops working. I found the environmental spec for this product, and it says 20 minutes at 80 degrees, 5 minutes at 150 degrees, 150 degrees and 2 minutes at 315 degrees. Now, so I imagine that's probably Fahrenheit, but obviously those are pretty high temperatures, and I know from previous experience that that is the sort of temperature that fire equipment does actually have to deal with, because obviously the guys are wearing fire suits and protective suits. Let's take a trip around the main board. This is the video out socket. This is I think a filter inductor for EMC filtering, so obviously the video camera's going to have a cable coming out of it, and that's potentially a source of noise out, but also I think in this application noise in, because it gets, say if a guy's using a two-way radio and the camera cable's close to it, you could potentially couple quite a lot of noise into the system from there. And there's another one of those on the other side. I'll not forget, as well as video, there's another 2 connections coming out of here. It could just be power, there may be some sort of input as well for some sort of switch. Haven't really looked into that yet. That's just the connector for the big logic board front end assembly. Just a few little analog bits here. That's the power connector for the sensor head. And we've got the display. I actually found the data sheet on this. This is a Sony little TFT module there's very little logic on here. There's a couple of on the other side there's a couple of dedicated driver chips as well, and around here this is all power supply, a couple of big capacitors, and the rest of these are just all switch mode regulators to provide various power supply rails. These will be sort of transient protection on the battery for things like static discharge and general battery issues, make sure it doesn't blow anything up. And these are the spring contacts that make contact with those. On the other side, so we've got all this power supply stuff. There's a precision reference and a multi-channel A to D converter here. Not entirely sure what that's doing. It may just be monitoring all the system voltages and a few other odds and ends. There's an audio amplifier chip. This is close to what looks like the backlight power supply for the display. There's a big inductor on the back side, and that inductor actually the top of it looks like it's actually slightly tilted, so that might also have been a casualty of it having been dropped. So we'll pull that apart in a minute, take a look at that. Then we've got these 2 Sony chips. These are dedicated support chips for this display, so this whole thing is just going to be the head-up video monitor stuff. Down here we've got a whole bunch of various analog stuff, a couple more inductors. I think this is generating the power rails for the sensor, because these are fairly close to where the sensor connects in. Little string of status LEDs there. There's another multi-channel A to D here. Again, that's maybe just monitoring various things about the sensor, don't really know. But there's quite a lot of op amps, a few MOSFETs down here. There's a multi-channel D to A converter here. Again, that's probably for setting the voltages to keep the sensor happy. Another 24C01E squared prom, there's one on every board. There's 2 of these. These are high-speed video D to A converters, so these will be for generating the video signal. I'm guessing there's 2 of them, one to drive the internal monitor and one to drive the external video. They probably run at different frame rates. And these are video field memories. They're sort of specifically designed for video, so these are going to be again producing for the display memory for the 2 displays. And probably 1 for the internal display, maybe 2 for the external. I don't know what the relative resolutions are. Or actually it could be 1 for RGB, come think of it, these are RGB DAC, so perhaps we've got 1 for each primary colour. This is a PAL NTSC video encoder to encode the composite video for the external monitor. Right, I figured out what was wrong with this backlight driver, this transformer that drives the backlight thing. I was a little bit puzzled by sort of one of the descriptions of the eBay seller saying that he'd found a bit loose inside and put it back. Actually what it looks like, it was this top coil that was loose and it's just been glued back. You can actually just about see the ends of the wire, like there. Obviously this thing had just, when this thing got dropped, this whole top just detached and pulled all the wires off the pads. So we need to see if we can do a little bit of fine surgery to reattach those. Right, I just very carefully with tweezers just sort of teased out each of the wires. There's 4 wires, it's just a primary and a secondary. If you look at the PCB, you see 2 are connected together, and I've just checked that these 2 are connected to the backlight connector. I imagine this is going to be a step up, so I should be able to figure out which is the primary and which is the secondary and how it's wound. And because these wires are so fragile and the base isn't in a particularly good condition, there's actually quite a lot of room on this PCB. So because there may be some uncertainty on the connections, I think what I'm going to do is I'll just glue this the wrong way up next to the footprint, because there's plenty of space around here on the board, so I can then just connect wires from there across to the pads, and it gives me a chance to experiment in case they're not all correct. Right, I've soldered some wires onto the ends of these. Obviously these are very thin wires and very susceptible to snapping, so what I'm going to do, I've done these sort of cross wires, so I'm just going to blob the whole lot in clear epoxy to just basically stabilise it to avoid any risk of it snapping. So if I sort of blob epoxy over the middle of that, then there's enough length of wire under the epoxy that any bends on the wire externally aren't going to find their way to the fragile ends and snap off. Right, while I'm waiting for that epoxy to set, just take a quick look at the charger. Nothing particularly exciting, sort of 4 batteries, and this just looks like there's 4 pretty much separate circuits. There's a mains input, protection diode, there's a PIC 16C54 on there, which I'm guessing is probably talking to this BQ 2014 gas gauge chip within the battery pack. Linear Tech battery charger. There's these spring contacts. There's the sort of spring contacts on the bottom go through the board, and then they're just attached with wires and these little loops to minimise the stress on it. Nothing particularly interesting or exciting there. Oh, one other little detail though, this is obviously painted bright fire brigade yellow, and these screws, obviously it might be actually screwed down to the fire engine. Someone's actually gone to the trouble of painting the countersunk screws yellow, just to make sure the whole side looks yellow and there's no silver bits there. Right, now we've got a nice epoxied coil with the leads all nice and stabilised, so we can safely play with them. So let's figure out which is the primary and the secondary. Just measuring the resistance. 17 ohms across to there, and 10 ohms, no, 1 ohm there, so that's going to be the primary there. If you've got a transformer where the ratios aren't quite so big, then measuring the inductance will give you a pretty better discrimination between primary and secondary, but this is obviously clearly a big turned ratio, so you can just do it by the resistance. Right, that seems to be working now. Little detail here, you can see this is actually an 8-layer board. Not really sure what this display is. I'm guessing it's maybe some sort of planar cold cathode. You've got these 2 sort of electrodes going into the glass, but there's also these electrodes on the back, which I'm guessing are some sort of capacitive coupling or something. Very odd. Right, I just fired it up and noticed that the clicky thing wasn't clicking and the display wasn't working. Then I remembered I hadn't actually put this repaired coil back on yet, so maybe that will help. Right now, we've put the coil back, let's see what happens. Right, we now appear to have a cute little display working, and clickiness. So that looks like it's all working, and we can actually put it back together again. Alright, that's it back together and all working. And you might just be able to see this head-up display thing, apart from seeing the just about see it. I just had a quick walk down the garden at night. It's not that impressive as a display, to be honest. Maybe it takes some getting used to, or maybe it works better if it's clipped to a helmet, but I think the combination of the weight and the visibility means it was maybe not a particularly successful product. Right, it's doing a little mod here. These batteries are a bit of a pain in the arse to get on and off. You've got to lift these 2 flaps, these 2 latches to get it on and off. It's a bit of a pain, so I've just added an on-off switch, just a little rocker on-off switch. Unfortunately I've obscured the legend, the colour legend, but they spelt it wrong, so not too bothered about that. And because of these spring contacts, what I've had to do is actually drill out these 3 wires and just solder to the edge of the pad, and then just cut away the edge so that I can connect to that pad to interrupt it for the on-off switch. I've also added a little DC power input jack so I can run it from a mains power supply. I didn't want to use the cutout on that because of potential voltage drop at the sort of 1 amp power draw, so what I've done is I've actually put it in the battery space so you physically can't plug anything in if there's a battery in there. And one other little mod I've done, the lens had a sort of fairly fixed adjustment. There were like two little holes in the mount, and there's an Allen key there to lock it, because obviously they wanted a fixed field of view, but I wanted to be able to adjust it, particularly to focus on things closer up, so I just fixed this knurled ring on there. There weren't any screw holes in the lens. I just basically using these screws as studs and put some metal loaded epoxy to sort of basically stick it into the holes, so I can actually adjust the focus quite easily now, because it's quite stiff. They've probably got some sealant or something inside there, so it's actually quite hard to turn. I'm sure I'll be doing a few videos of fun things you can do with a thermal imaging camera in future, but I just want to do a few quickies. One thing is that what I was saying earlier about very few things being transparent to infrared. Here we've got a sheet of glass, but infrared, almost opaque. You can see some reflections off the surface, but you just can't see anything at all through it. I'm sort of waving behind your front, nothing. This piece of plastic, transparent plastic film again, a little bit of transmission through it, but the other thing is if I put my hand on it to actually warm the surface of it, you can actually see the heat from the surface. You can actually write in heat files. That also works on paper, in fact. So you've got obviously a piece of paper that's fairly well insulated, so you don't see anything through it. But if you put your hand behind it, you can actually create sort of a heat path, just purely because your hand is heating up the surface of the paper. A few special materials here. This is a small germanium window, which you can see is pretty much opaque at visible, but at infrared, let's put that right over the lens, there's some attenuation, but it's still, you can still see quite a lot through it. This is a zinc selenide lens. This is the sort of lens that's used in a CO2 laser cutters and medical lasers. And again, this has got very good transmission, because of course a laser, you don't really want to absorb energy in the lens. So if I just stick that over the lens, obviously it's going out of focus, but it's got a fairly decent amount of transmission at that wavelength. Wavelength wise, we're talking, I mean, CO2 laser is about 10 microns, so thermal imaging is in the sort of 8 to 15 micron sort of range of wavelengths. So that's about a factor of 10 longer wavelength than visible light. Another piece of plastic, this is a piece of probably ABS plastic again, pretty much, so there's some finger marks on it. You can actually see sort of residual heat paint. If I put your finger on it, you actually see the residual heat footprint on it. This is a piece of sort of fairly thick acrylic, and again sort of pretty much opaque. This is the lens from a PIR alarm sensor, which is polythene, which there is a certain amount of transmission through. You might just about be able to see some lensing effect, but I think the lensing effect on that's fairly strong, so you see, you can actually see through it. And the thin polythene sheet is actually fairly transparent. It's one of the few materials that is actually quite transparent, so you can see there's a little bit of attenuation, but you can still see quite clearly through it. And even polythene that's not visually transparent, it's actually quite transparent is infrared. This is black plastic bin liner, and again you can see there's actually quite a lot of transmission through that. And of course we can look at the temperature of things. So for example, here's a piece of ice, looks sort of black. Soldering iron, which obviously starts looking a bit like a lightsaber, so it's a bit on the hot side. One interesting application in electronics for thermal imaging is finding short circuits, looking at the heat generated by current flow. I've just got a PCB here. I'm just going to stick about an amp through one of the tracks on it, and you can see almost instantly it lights up, and you can actually see the current path along the track pretty much instantly. Quite cool. It's very handy for tracing sort of a fault on a large PCB. Something else I read about, I was just looking sort of vaguely on the net about thermal imaging, and someone actually proposed using a thermal imaging camera as a hack for finding people's credit card PIN numbers. Now I haven't actually got the rest of the PIN terminal that I tore down a while ago, but this calculator's got a very similar sort of rubbery keyboard. The idea is that if you sort of type a number onto it, the heat from the fingers stays on the keys. So if you actually look at this thermally, you can actually see hot spots on the keys that have been pressed, and you could probably, by looking at the decay rate, actually figure out which order they were pressed in. And if you want to look cool in thermal imaging, all you need is a pair of normal clear safety glasses.